In this outcome, we're going to deduce the Lewis electron dot structures of molecules and ions for up to 4 electron pairs on each atom. So let's briefly just talk about what do we mean by a Lewis structure. Well, what we do is we take the element symbol and then we take only the valence electrons and represent them, because the valence shell is the one that's involved in the bonding. So for example, hydrogen, it has only one electron. So we usually represent the electrons by either circles or X's. Now carbon, for example, is in group 4. It has 1, 2, 3, 4 valence electrons. And this is how we distribute them. You think of it as 4 sides. You have to distribute 1 to each side first. And the next one, nitrogen, is in group 5. So 1, 2, 3, 4, and then now I don't have another side to put it on, so now I can start pairing up. And I could have paired them up on any of the sides, but I chose the top. Oxygen's in group 6, so we go with 1, 2, 3, 4, and then 5 and 6. So you'll see here that I put them opposite. That's sort of just to represent that I understand that electrons repel each other. You don't necessarily have to do that, but I think it's good to think about that. And each of these, every time we have 2 like this that are paired, we call them lone pairs. And let's just take a look at fluorine quickly. Fluorine is in group 7. 1, 2, 3, 4, 5, 6, 7. All right. Now, something to note is that as we go down, for example, phosphorus is still in group 5, so it has exactly the same Lewis structure as nitrogen. And sulfur is in group 6. It has exactly the same Lewis structure as oxygen. And then all of the halogens have the same Lewis structure as fluorine. I'm not going to draw that one in. They all have 7 valence electrons. So these are our puzzle pieces, essentially. We're always working with covalent compounds with Lewis structures, so we're working with these nonmetals. We need to fit these together so that all of their valence shells are full. Hydrogen only needs 2 to fill its first energy level, but the rest of these need at least 8. And we're only going to focus on the 4 electron pairs, the 8 this time, and there will be another video for HL where it goes beyond that. So in other words, we need carbon to have 8, nitrogen to have 8, oxygen to have 8. So we're going to start bonding until everything has a full, what we call octet, a full octet, and we'll show you what that means. So the first thing we're going to do is we'll look at water here, and our first step is to start with the element that can create the most bonds. Well, we have a hydrogen, which can only create 1 bond, and we have oxygen, which can create 2 bonds. It has 2 places where it can gain some electrons. So we'll start by putting oxygen in the middle, and again drawing its Lewis structure. 1, 2, 3, 4, 5, and 6. And try to be really neat. It's hard for me to draw with this, but try to be as neat as you can. Now I'm going to start using X's for my hydrogen, so I know where the electrons came from. The circles will be from the O, and the X's will be from the H. So this electron here is represented by an X now. So hydrogen bonds with oxygen here, and now hydrogen has 2, so it is stable. Oxygen still only has 7. It's not stable, but luckily we have another hydrogen, so we're going to do that there. The fact that they ended up being opposite doesn't matter, as long as you have them 2 side by side shown like that. So that would be the Lewis structure for water, and usually at the end we end up representing these bonds, these covalent bonds, as lines. So our final answer would look like this. So the line represents these 2 that were being shared, and these 2 lone pairs, you still must put them in. If you forget to put them in, then you will get a mark taken off. Okay, let's start now with CCl4. So carbon has 4 possibilities. Chlorine is one of the halogens, so it's like fluorine. We can see there's only one place for it to bond. So carbon's going to go in the middle, and we go 1, 2, 3, 4. And now we start taking our chlorines and try to make them complete the octet. So chlorine, everything else will be filled in now. Okay, just like that. And now we have another space here for chlorine, another chlorine. So we fill that all in. Okay. And so these two chlorines are stable. They have 2, 4, 6, 8, 2, 4, 6, 8, but our carbon still only has 2, 4, 6. So that's okay because we still have some more chlorines we have to add. And the last one over here. Oh. Alright, so this is our Lewis structure, and this carbon now has 8, so everything is stable, so we know we're correct. That's the great thing about Lewis structures. As long as you count and everything works, then you can't be wrong. Alright, over here we're just going to quickly draw that out as a final answer. So carbon with chlorine, 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 chlorine. And again, each line is representing that covalent bond. But the most important thing you have to realize is you have to rewrite all of these lone pairs. So if you forget to write all of those lone pairs out, then you're going to end up losing marks. So make sure you do not forget that. It's really, really easy to do that. So get yourself practiced with writing them all in again at the end. All right, so now we're over here, nitrate. So now we're starting to get into ones that have charges. So keep charges in mind because they're what we call the wild cards. In other words, this negative tells me that there's an extra electron that I can use whenever I want to make my structure work. And now that I'm thinking about this, we might have to think about using double or triple bonds to make it work, or dative bonds, and I'll show you what that means when we get to one. So let's start again. Nitrogen is going to make the most bonds because it can make 3, 1, 2, 3, 4, 5. All right, so let's take oxygen. Oxygen is going to try and bond here. And that's a little misaligned. Let's try that again. Okay, and oxygen has 6. So I'll use 1, 2, 3, 4, 5, 6. So over here you see that oxygen still only has 7. So what I can do is I can use my wild card, my extra electron, and fill that in. Now that I've used it, I can't use it again though. So now when I get to my next oxygen, okay, I have to think about what's going to happen because I know that I'm going to end up with this one over here again, but I have no extra electron left. So now, since I don't have that, I have to start thinking about making a double or triple bond. So anytime we do that, all we do is we take one of the electrons and move it in. So I'll move it into here. So this is now up here. And then we have to take another one from nitrogen and move it down into there to make a double bond. So now these two electrons have moved, and now they're in here. We formed a double bond. So if we count, this works because this oxygen has 1, 2, 3, 4, 5, 6, 7, 8. All 4 of these count when we do this. Now nitrogen, if we count, we also count those 4. So it has 1, 2, 3, 4, 5, 6, 7, 8. Nitrogen's stable already. Oxygen's stable already. But we still have one more oxygen to add. So I have to think to myself, well, is there anywhere to bond? Well, no, there isn't. There's no one electron. So this tells me that there's going to be a dative bond. So what I really need to do is I need to think on the side what I can do with my oxygen, which is 1, 2, 3, 4, 5, 6. What I can do is I can move this one to the end like this, and then I have those other ones that were already there. And now these two electrons fill in and make the dative bond. In other words, a dative bond is both electrons that are used for sharing actually come from one of the atoms. So now this oxygen has 8 and nitrogen still has 8, so everything's balanced. Now let's draw the final answer for this. So here's our double bond. So we show that with double lines. So each line represents 2 electrons. And then we have our oxygen, which again, we need to put our 2 lone pairs. And then this nitrogen over here had just a single bond. So you'll see that this one, you only drew 2 lone pairs because there's a double bond. Here you have the 3 lone pairs. And then this one up here, because it's a dative bond, the dative bond needs an arrow pointing towards the one that was accepting, so, or away from the one that was donating. Depends what perspective you prefer. And so then we fill in the rest. So this is the key to why this method of just playing around with it is necessary, so that you can see this dative bond, when does it happen. And let's do one more example here, H3O. So that's just like our water over here. So I'm just going to bring that on over so that we can use it again. And there we go. So what happened here is, again, okay, so I have a charge here. So that tells me, since it's positive, I have 1 less electron. So I can use that to make it work. And I have to attach 3 hydrogens. So I start with the water, and everything is working right now. There's actually no place for another hydrogen to bond. If we think about it, okay, the hydrogen, it's right up here, has 1 electron. But since I have my wild card here, this can be gone. So I can just attach an H with a dative bond so that both electrons come from that oxygen. So when we draw this one out, it'll be H, H, and then this one will be dative. So we put the arrow on it, and then we can't forget this lone pair, because if we forget that, we lose a mark. All right, last step. We have to put the charge on it. This was a plus, and also on this one, we have to make sure that we put the square brackets, and then this was a negative, negative. So that's the process, and I suggest doing this so that you can definitely see where the dative bonding comes in, because every once in a while those types of questions come up, and if you use some of the shortcut methods from other books and you only practice those, you're not going to get the dative bond question.